This is going to be a lecture about using the American College of Sports Medicine metabolic equations. And we'll go through several examples, and I'll give you some practice problems also to make sure you know how to use these. So, the purpose of these calculations or these equations is basically to estimate energy expenditure during steady state exercise. So, if you were jogging or walking at a steady state, you should theoretically be able to estimate how much energy you're expending based on that workload. Same with cycling, same for stepping up and down. But the key is you have to be at a steady state for these equations to be accurate. So, as far as the units go for these metabolic equations, we're going to focus a lot on oxygen consumption. So, quick review of some exercise physiology. When we assess oxygen consumption, we can measure it in either absolute or relative units, or we can report it in absolute or relative units. So, absolute units are independent of body weight, and the units are generally liters per minute of oxygen, liters of oxygen per minute. You could also report this as milliliters of oxygen per minute, but liters is a little more common. Relative units are relative to body weight. So the units would be milliliters of oxygen consumed per kilogram of body mass per minute. This is good to use when you're comparing oxygen consumption between people of differing body weights. So you should be able to convert back and forth between absolute and relative units, and you're going to have to do some of the problems that we're going to go through. So this is a quick question or problem where you need to convert between absolute and relative units. So if a 50 kilogram person and a 70 kilogram person have the exact same absolute oxygen consumption, maybe they're working on a treadmill or bike or whatever, but their oxygen consumption in absolute units is 2 liters per minute, and I'm just making that up, 2 liters per minute. Who has a greater relative VO2? So to answer that, we would need to convert between absolute and relative units. So an easy way to do that is I always like to take it one step at a time and convert the liters to milliliters, or if you go in the opposite direction, milliliters to liters, because that's an easy conversion instead of trying to do too much at once. So 2 liters is 2,000 milliliters. So we could just rewrite 2 liters per minute as 2,000 milliliters per minute. And then we just divide by the body weight. So 2,000 milliliters per minute divided by 50 gives us a relative VO2 of 40 milliliters per kilogram per minute. And for the 70 kilogram person, 2,000 divided by 70 is 28.6 milliliters per kilogram per minute. So you can see that the person who weighs less is always going to have a higher relative VO2 if their absolute VO2 is the same. So gross versus net VO2 refers to whether or not you're including resting metabolism. So this is important when you're thinking about energy expenditure goals for maybe weight loss and how much energy is expended in a given exercise bout. So a lot of times you want to know how much energy you expended or how many calories you expended due to that exercise bout you did, not only due to resting metabolism on top of that. So let me try to explain what I mean by that. So gross VO2 is your overall oxygen consumption. That includes what you're consuming due to any physical activity and also what your body is using at rest. So we generally assume that resting VO2 in relative units anyway is about 3.5 milliliters per kilogram per minute, and that's what we call 1 met. But so let's say if you're walking down the street and your VO2 is measured as 6 milliliters per kilogram per minute, then that 6 actually not only includes the energy that you're using to walk, but also what is used at rest. So that overall energy expenditure would be the gross VO2, or that overall oxygen consumption would be the gross oxygen consumption. Net VO2, on the other hand, is the VO2 in excess of resting oxygen consumption. So again, back to that same example, if we assume resting oxygen consumption is 3.5 and you're walking slowly down the street and your VO2 is measured at 6, that gives us a net VO2 of about 2.5. So it's in excess of resting metabolism. So, simple equation, the net oxygen consumption is gross minus the resting oxygen consumption. So as far as metabolic units go, I just wanted to bring up this concept of METs, or metabolic equivalents. You've probably heard this before, but it's pretty simple. 1 MET is supposed to be your resting metabolism. 2 METs is 2 times your resting metabolism. 10 METs would be 10 times your resting metabolism, and so forth. So there is a way to, there is a standard conversion between METs and oxygen consumption, and so we assume that 1 MET is about 3.5 milliliters per kilogram per minute of oxygen consumption. So with that being said, it is an assumption. So not everybody has a resting metabolism of 3.5 milliliters per kilogram per minute. But if you average out thousands of people, that's about what the average would be. So as far as units of energy expenditure, kcals or kilocalories is how we're going to measure it, and we're going to generally report it as kilocalories per minute. So our units of energy are mainly going to be kilocalories or kilocalories per minute. So this is useful as it has implications related to weight control and energy balance. So it's estimated, and it's not a perfect estimation, but it's still commonly used that to metabolize a pound of fat, or if you wanted to lose a pound of body fat, you would need to have a negative energy balance of about 3,500 calories, meaning you would have to burn about 3,500 calories to lose a pound of body fat. So it's not a perfect conversion, but for the most part, it's still commonly used, and it is a relatively good estimate if you look at an average of the population. All right, so relationship between VO2 and caloric expenditure. 1 liter of oxygen consumed is about 5 kcals. So, in other words, we can say we expend about 5 kcals per liter of oxygen consumed. And we commonly call this the caloric equivalent of oxygen. So, liter of oxygen is about 5 kcals. So, if you wanted this conversion, and 5 is kind of like a magic number here. We're always going to use a caloric equivalent of 5. Some people use 4.875, 4.75, and I'll elaborate a little bit more on why that might be, but we're going to use a nice round number of 5 for this. So basically that we could use that to see how to convert oxygen consumption to kilocalories. So if your oxygen consumption, for instance, was 2 liters per minute, we could use that caloric equivalent and say that 2 liters per minute times 5 kcals per liter gives us about 10 kcals per minute. So we just converted oxygen consumption to kilocalories per minute. So back to that topic, it's not really overly important, but you may see this in the textbook that some people use a number that's a little less than 5. It has to do with what substrate you're using, so fat versus carbohydrate. So carbohydrate is a little bit more efficient, so it's going to give you about 5 kcals per liter of oxygen consumed, whereas fat is a little less efficient, and it's going to give you about 4.68 in that ballpark kcals per liter. So you could take a halfway point between that, which is what some people do, or you could just estimate it and know it's an assumption that you're going to be expending mostly carbohydrate, and the error is relatively minimal, and so that's why most people go ahead and use 5 kcals per liter as the caloric equivalent, and that's what we're going to do. So other conversions, 1 MET is about 1 kcal per kilogram per hour, less commonly used, but it's there if you ever need it. And then, so one way you could use this is, say, if you're thinking of your resting metabolism, which should be around 1 MET, if you weigh 80 kilograms, you would, just due to your resting metabolism, you would expend about 80 kilocalories per hour. So when we try to determine the caloric cost of an activity, like how much energy are you expending jogging or walking or riding a bike, we want to make sure we're using net VO2, because what we're concerned with is how much energy we're expending in excess of resting metabolism. Because you're going to spend your resting metabolism regardless if you're sitting on the couch or exercising. So what you're commonly interested in is how much energy you're expending on top of or in excess of your resting metabolism. So we're going to now go through the different equations that are in the American College of Sports Medicine book. So we're going to do a walking, running, cycling, arm ergometry, and then stepping. So this is not high-powered math, so I'll probably give you more information than you need to know here. But the way the walking and running equations are set up are there's a horizontal component, there's a vertical component, there's a resting component. The resting component is always going to be 3.5. The vertical component assumes you're walking up an incline. If you're walking on a flat surface, this is going to be 0. Horizontal refers to the speed. All right, so with that being said, this equation is going to give relative VO2. All these equations are going to give relative VO2. So if you need absolute, you're going to have to convert it after the fact. So here's the equation. VO2 equals 0.1 times speed plus 1.8 times speed times grade. Grade is the incline. And then plus 3.5, which is your resting component. Now the tricky part of this is the speed has to be in certain units. So the speed needs to be in units of meters per minute. The grade needs to be as a decimal point. So if you're walking up a 2% incline, it would be 0.02. And so that's how it goes into the equation. But you do need to convert. If you have miles per hour, you have to convert it to meters per minute. And I'll show you how to do that. If you're interested in where the constants come from, they're here. It's not overly important, but if it just gives you an idea of where these numbers are coming from and whether or not, and just let you know that there is some scientific merit to these numbers. They're not just made up. So if we want to do an example, what's the oxygen consumption for walking 3 miles an hour up a 5% grade? First thing we have to do is convert into to the right units. So here's that conversion for miles per hour to meters per minute. It's 26.8. I would always give that to you if you needed it on an exam. But so 3 miles per hour times 26.8 gives us 80.4 meters per minute. And that 5% would go in as 0.05. And then we just plug in place. So we had 0.1 times speed, so 80.4 plus 1.8 times 80.4 times 0.05, and then we add the resting component, all these together, get about 18.8 milliliters per kilogram per minute. If we wanted to convert that into METs, which is common, we could just divide by 3.5. It gives us 5.4 METs. Simple enough. Running equation, very similar setup. The big difference is the constants. So you technically need to be going over 5 miles an hour for this equation to be accurate. But set up exactly the same way. As you can see, only the constants differ. Everything else is the same. So as far as the constants, this is where they come from. If you're curious, not a big deal, but the important thing is to know that this is the equation and know how to use it. So let's do a quick example. 6 miles an hour, 5% grade. Convert 6 times 26.8. That conversion factor is the same. I got 160.8 meters per minute. 5% again goes in as 0.05. And we just plug in the numbers, and I get 42.9 milliliters per kilogram per minute. If you wanted to convert that to METs, you could. Just same thing, divide by 3.5. I get 12.3 METs. All right, moving on to the ergometry equations. This could be cycling, which would be leg ergometry, or even arm ergometry, and there are separate equations. So this setup is completely different. So you have to calculate the power, or what is commonly referred to as work rate, and the units have to be in kilogram meters per minute. This is not common for a lot of people. A lot of people are used to the unit of watts. So if you have power output in watts, you would need to convert it into kilogram meters per minute for this equation to work. And so the conversion is 1 watt is 6.12 kilogram meters per minute. That's a standard conversion. So the way this is set up, though, work rate or power, when you're doing ergometry, let's just assume leg ergometry right now that everybody can envision. It's the power or work rate is determined by the resistance that you're pedaling against times the distance. The distance refers to how far that the flywheel would go if it during one revolution. So if you took the flywheel off of a stationary bike and rolled it where it rolled over one time and measured that distance, that's the distance we're talking about. And it's pretty easy because it's going to be consistent for us. Frequency refers to revolutions per minute. So basically how quick you're pedaling, how many revolutions per minute. So the resistance is basically the force setting. And this, it's going to mainly go in kilograms, but you may also see kilopond. Kilopond and kilogram are a little bit different, but they're close enough where it doesn't really affect the outcome here. So kilopond is basically takes into account the effect of gravity acting on a 1 kilogram mass. It's going to make a slight difference, but so kg and kp, if you see kp, we're going to use those terms synonymously for these equations. So resistance is the force setting either in kg or kp. Frequency is the RPMs, pedaling frequency. The distance is how far that wheel goes in one revolution. And if we're always going to be talking about monarch ergometers, so if you're using a monarch leg ergometer, like a stationary bike, the distance is always 6 meters. If you're using an arm ergometer, it's 2.4 meters. And those are always going to be the same. So here's the cycling equation. Also going to give relative units. It gives a range of where it's most accurate, 50 to 200 watts. So here's the equation. So VO2 equals 1.8 times work rate. So work rate is what we just talked about calculating, divided by your body mass in kilograms, so your body weight in kilograms, plus 7. So if you want to know where these constants are coming from, here it is again. And this 7 seems like it comes out of nowhere, but really that includes the resting component and also the cost of unloaded cycling. So that 3.5 and 3.5 give us that 7. So this equation still does take into account the resting component. So let's do an example. So VO2 what's the VO2 for an 80 kilogram person cycling on a monarch leg ergometer at 50 RPMs with a 2 kilogram load? So the first thing we need to do is calculate the work rate. Relatively simple, 2 times 6 times 50 gives us 600 kilogram meters per minute. And then we plug that into the cycling equation. We get 1.8 times 600 divided by 80 plus 7. Let's do this step by step. I got 20.5 milliliters per kilogram per minute. And then again, if we wanted to convert to METs, divide by 3.5. All right, the arm ergometry equation, really similar. It's actually the exact same except for the constants, and obviously the distance is going to be different. So 3 is the constant here times work rate divided by body mass plus 3.5. So 3.5 is the resting. So if you're using the arms, it's been noted that the oxygen cost of unloaded cycling with arms is pretty much negligible. So it doesn't really require any energy. At least that would affect the equation. So we just go with 3.5. So example, VO2 for a 70 kilogram person working on a monarch arm ergometer at 50 RPMs, 1 kilogram load. Calculate that work rate. 1 times 2.4 times 50, I get 120. And then we plug that in with their body weight and get 8.6 milliliters per kilogram per minute. Want to convert to METs, divide by 3.5, and there we are. All right, last equation, the stepping equation. So step rates of 12 to 30 steps per minute is where this is going to be accurate. Step heights anywhere from 0.04 to 0.4 meters. Gives you an idea. So pretty wide range of stepping heights here. So it's going to give us a relative VO2 again. Similar to the walking and running equation, we have horizontal, vertical, and resting components, but this equation is going to look really different. So here it is, 0.2 times step rate. So the step rate refers to how many steps per minute, and that includes a 4-step cycle. So, in other words, if you were stepping up on a step and then stepping back down, so up, up, down, down, that's one step. And however many times you did that cycle in a minute, that would be your step rate. The then 1.33, which is a constant, I'll explain in a minute. 1.8 is there. Step rate times step height. Step height has to be in meters, and here's also your resting component again. So the constants, if you're interested where they're coming from, the 0.2 is a horizontal stepping, 1.8 vertical stepping. The most interesting part of this is the 1.33. That adding that 0.33 takes into account the eccentric work. So in other words, you have to think you're not only expending energy to step up, but you're also expending energy to step down. And it's always estimated that eccentric work is about 1/3 of the energy cost of positive work. So that 0.33 is taking into account the energy expenditure of stepping down. All right, so for example, if we had a 12-inch bench, 30 steps per minute, we just have to convert that that step height in inches to meters. We get 0.3048, and we can just plug in the rest. See where we end up. 31.4 milliliters per kilogram per minute. If we wanted to convert to METs, divide by 3.5, get 8.9. All right, so shifting gears a little bit. So we've gone through all the equations. If you need caloric expenditure, remember that we have to use that caloric equivalent of oxygen. And then also, unless you are told otherwise, you generally want to focus on the net VO2 because you're interested in that energy cost in excess of resting metabolism. So a 70 kilogram person is exercising a VO2 of 30 milliliters per kilogram per minute as measured on a metabolic cart. So if it's measured directly on a metabolic cart, that's gross because you're just directly measuring oxygen consumption. That includes rest. So that's gross VO2. So we want to know what their caloric expenditure is in net terms. So first of all, we convert that gross VO2 to net VO2, and we just subtract out the resting, and we assume it's 3.5. We're always going to assume that unless you're told otherwise. So we get a net VO2 of 26.5. And then we need, before we can use that caloric equivalent of oxygen, we have to get it into absolute units of VO2. So this is relative units right now. So 26.5, we have to convert that to absolute units. Just like I did earlier, I always do the simple thing first. So we convert the milliliters to liters. So I get 0.0265 liters per kilogram per minute. And then we multiply by body weight. Take that 0.0265 times body weight. That gives us 1.855 liters per minute. This is our absolute VO2. And then we're home free. We just have to multiply that by the caloric equivalent, which is always going to be 5 for us. So 1.85 times 5, 9.3 kcals per minute. That's the net caloric expenditure or energy expenditure at that intensity. All right, so we're going to go through a few more practice problems here. And then I'll give you some to practice on your own. So we'll look at these case studies. So calculate the net caloric expenditure for a 75 kilogram person exercising at a gross VO2 of 17.4. So if we have that gross VO2 of 17.4 and we want to get their net kcal, the first thing we want to do is get this VO2 into net units. So the gross VO2 is 17.4. The net VO2 is, to get it, we just subtract 3.5. Now we have 13.9. So then we're good to go. We take that 13.9, need to convert it to absolute units. Easy step first. Convert to milliliters to liters. Multiply that liters per kilogram per minute times their body weight. We get 1.04. So this is our absolute VO2. And then to get kcals, we just multiply that by 5. That's our caloric equivalent, always going to be. And we get a net energy expenditure of 5.21 kcals per minute. intense here with but you should be able to figure this out. You just have to think about this. So you're going to see a lot of questions like this where you actually have to think through it and use the equations accordingly. So let's say you're prescribing exercise for someone and you determine that they need to be expending about 300 kcals per session, and that's net. So I put 300 kcals per session in excess of resting metabolism, which is a fair amount. So assuming that what this person can do is walk on a treadmill at 3 miles an hour, 0% grade, and that's what they're comfortable doing, we want to know how long they need to do that for each session to hit that 300 kcals. So we can actually calculate that. So what we want to do first of all is calculate how much energy they're expending at that intensity, at the 3 miles an hour. All right, so I'm going to use the walking equation because that's what they're doing. And I put in the speed, 3 miles an hour, convert to meters per minute. And then notice I put in a 0 for the grade, so that's going to make all this go to 0 because they're walking on flat surface. And I got rid of the resting. That's a simple way to get it into net units. So instead of calculating it in gross, getting a gross VO2 and then subtracting out the 3.5, which you can do if you want, I'm just going to not add this to it, and that's automatically going to give me net VO2. So I get a net VO2 of 8.04 milliliters per kilogram per minute, and then we need to get that into kcals. So convert this relative VO2 to absolute VO2, and two-step process. If you follow this, I get 0.64 liters per minute. So that's the absolute VO2 associated with that workload. So to get kcals, multiply it by our magic number of 5, we get 3.2 kcals per minute. So that's what they're expending. At 3 miles an hour, that's their net energy expenditure. And so to see how long it's going to take them to get to 300 kcals, we just divide 300 by 3.2. And that gives us a pretty high number of 93.8 minutes. That's how many minutes they would need to walk on that treadmill at 3 miles an hour to hit that net caloric goal of 300 kcals. So that seems like a long time. So I'm going to ask a question, how could you decrease that? Because that's probably the first question they're going to ask. What can I do to not exercise for 93 minutes each time? Well, the simple answer is just work at a higher intensity. So if they can't walk any faster, so 3 miles an hour is a pretty good pace for a lot of people, well, you could increase the incline. So that would probably be the next step. So I'm going to give you just a follow-up question. Let's just see how big of a difference this made. So same question. This time we're doing it 2% grade, which isn't a big incline, but so it's doable for most people. We could do the same thing and see what a difference it makes. And we got it down to 69 minutes. So you could keep playing with these numbers. So maybe increase the speed a little bit, increase the grade a little bit more, and you gradually are going to see the time requirement come down to hit that caloric goal. So that's why it's good to be able to kind of think through these problems so you can figure things out if necessary. All right, so another study, this one to do with cycling, or another case study. Calculate the oxygen cost of pedaling 75 RPMs on a Monarch load setting of 3 kp for an 85 kilogram person. All right, so this one's going to be relatively straightforward. So the first thing we need to do is calculate that work rate. 3 times 6 times 75, 1350 kilogram meters per minute. This is our work rate or power. And we just plug that into the cycling equation, and we get a VO2 of 35.6 milliliters per kilogram per minute. All right, we'll do a couple more. This one's an interesting one because you're trying to figure out a certain percent of their max. So let me go back up. So just think about this question for a moment. So a subject 75 kilograms body weight has a functional capacity. This is the same as saying a VO2 max, so an aerobic capacity of 9 METs. Calculate a workload in watts on a Monarch ergometer that would be equal to about 70% of their capacity. So in other words, if you know someone's max and you decide that they need to exercise at about 70% of their capacity, what workload would they need to be at? So the way to do this, first of all, we know that 1 met is 3.5. So we could take that 9 mets and figure out their VO2 max. So we'll assume that if their aerobic capacity or VO2 max is 9 mets, we just convert that to units of milliliters per kilogram per minute. We get 31.5. And remember, we were trying to calculate 70%, so 70% of 31.5 is 22.05. And then we have to work backwards to get the workload. So here's our cycling equation. So we know the VO2 is 22.05. The 1.8 is a constant. Now we have to solve for work rate. So I'm going to put an X there. The body weight is 75. 7 is a constant. So we're basically going to solve for X. So move that 7 over here. That's 15. Divide these. That gives us 0.024X. And then we divide by 0.024 on each side. And we get X equals 627.1. That's the work rate. So, and then that's nice, but remember the question asked to put it in watts. So 1 watt is 6.12 kilogram meters per minute, and so in watts it would be 102.5. So that's one of the more complex questions that you might get, but by doing some simple algebra you should be able to figure it out. All right, we'll do one more. This one you have to think a little bit too. A cardiac patient who weighs 70 kilograms wants to return to work after having a heart attack. As far as, so you're trying to figure out if he or she are able to meet their energy demands at work. So the job description states that the energy expenditure is about 7 to 8 kcals per minute. So relatively manual labor type job. So the 7 to 8 kcals per minute includes resting metabolism. That's important so you can compare this. So this is a gross energy expenditure. So his aerobic capacity, our VO2 max, is 25 milliliters per kilogram per minute. And you got that off of an exercise test. That would be given to you also. So the question is he ready to go back to work? So how do you know this? Well, basically we need to see, there's a couple ways to do it. The way I'm going to do it is convert their VO2 max to units of kcals per minute. So if the aerobic capacity is 25 milliliters per kilogram per minute, we could actually convert that to units of kcals per minute. And so if we do that, it gives us an idea of if whether or not he's close to his max at work or not. So as a rule of thumb, we're going to say if you're ready to go back to work when your max is double what your energy capacity is at work. So if let's say his VO2 max, if we convert his VO2 max to kcals per minute and it was 16, that 7 to 8 is less than 50% of that, so he would be ready to go back to work. If it's not, then he's not ready to go back to work. That's 50% is not written in stone anywhere. I'm just saying that's what we're going to use as a guideline for our class anyway. So the way we could do this, I'll just talk you through it, is if the aerobic capacity is 25 milliliters per kilogram per minute, we just convert that capacity into units of kcals per minute, and we would get 25, convert it to, put it in units of liters per kilogram per minute, I would get 0.025 liters per kilogram per minute, and then take that 0.025 liters per kilogram per minute, multiply it by body weight, which is 70, I get 1.75 liters per minute as the absolute VO2, and then multiply that by 5 to get kcals per minute, I get 1.75 liters per minute times 5 is 8.75. So his capacity, his max, is 8.75 kcals per minute. And if at work he needs to expend 7 to 8 kcals per minute, he's pretty much being maxed out. So if that's the case, this person is not ready to go back to work, and it would this person would either have to wait longer and do more rehabilitation, or potentially find a job that has less of an energy expenditure.